Okay, so our last speaker of the day is Reynold. Reynold is a PhD student on leave from the AMP Lab. He's also a co-founder of Databricks and one of the core contributors of Spark, and he led the Shark project, and he's going to talk about a very cool sorting benchmark that he just embarked on today. So thanks, Reynold.
All right. Thanks for introing me. So Frank talked to you about sort of projects that could potentially save lives. So I'm going to talk to you about a project that hopefully maybe in the future enable other projects to actually save lives. Just before I really start, can I get a show of hands of how many people here that have seen some chart like this? I can't really see you at all now because of the light. I'm going to assume a lot of people put up their hands. And what about something like this? How many times have you heard, or if you have ever heard somebody telling you, oh, Spark uses a lot of memory and it's probably may not be a good fit for my big data? Again, I can't really see anything, but I'm going to assume some people put up their hands. It was actually sort of not so surprising, but I think for the longest time, the biggest misconception about Spark was that it is sort of a in-memory computation system, and it doesn't really work when your data don't fit in memory. And partially it's our fault. So initially, when we started as a research project, we pitched it as sort of a memory system. And when you see gigantic performance gains like this, a lot of it is actually due to the in-memory capabilities of Spark. Now, the truth is, Spark itself is actually designed as a very general sort of execution engine. It provides strictly a superset of what Hadoop MapReduce would actually provide. And so when as a matter of fact, the project goal of Spark, if you talk to any of the core people actually working on Spark now, they will tell you Spark really tries to work well for gigabytes of data all the way to maybe petabytes of data, and it should work well with different storage medium, including memory, disk, or SSDs for newer forms. And it should work well for sort of low latency streaming engines all the way to some very long running batch jobs. And for example, some of the longest running batch jobs I know in Spark runs for sort of weeks. Now, the last time I gave this talk in New York, actually in a different context, somebody asked me, pointed up their hands and had a very serious question. I have like kilobytes of data. What do I do? This is a good one. So I sort of since revamped the slide to add it. Now it's like going from kilobytes all the way to petabytes. So in order to sort of demonstrate essentially the first 2 points and about to counter the misconception about Spark only work well with data that fit in memory, we decided to participate in a third-party benchmark called the Sort benchmark. The Sort benchmark was actually originally proposed, I believe, by Jim Gray, who's a Turing Award winner that unfortunately passed away. Incidentally, also I think he was the first person that got a PhD degree from Berkeley Computer Science back in the 70s. So very well known for his work in databases and systems. This benchmark's been running since, I think, 1987. It might have been earlier than that, but the earliest record I could find was 1987. So it's running for about 30 years now, and there's a lot of participants from industry and from academia, and often the winners are using sort of purpose-built, sometimes definitely purpose-built software, sometimes even hardware to actually win the benchmark. And and I find it kind of interesting, sort of the rate the benchmark's been progressing. So initially, I think you were required to store a megabyte of data. And then over time, it grew to 100 megabyte. In 1998, this number went up to 1 terabyte. And in 2009, the number went up to 100 terabytes. So this number is keep going up. And the goal is to measure the advances of software and hardware. And this is one of the winning entry, I think, back in maybe 1998, about how fast it can. They sorted about 1 million records in a second. Whereas now, for 100 terabyte, you're supposed to sort, I believe, 1 trillion records. So we participated in the benchmark, and we picked the most challenging sort of category called Daytona Gray Sort. So Gray Sort itself is actually named after Jim Gray. And we sorted essentially the 100 terabytes of data in a fault-tolerant manner, which is what this most challenging category requires. And it is pretty interesting because sorting 100 terabytes of data actually requires us to read and write to disk for about 500 terabytes of disk I/O, and it also triggers 200 terabytes of network. The reason it has 200 terabytes of network instead of 100 terabyte is because you're supposed to replicate your output to make it fault tolerant. So by any measure, this is a fairly sort of resource-intensive job. And so the results, some of you might have already heard from news, because over a lot of media reports. We set a new world record, and it's actually tied with a research project from UCSD that's been doing high-performance sorting. And I believe it's the first time actually any system based on a public cloud infrastructure has won. But since 100 terabytes was kind of small, we felt, so we actually pushed the record. There's no official benchmark rule here, but we went on and sorted the petabytes of data on our own. So if you read the blog post I've written earlier, you probably found out about this. But essentially, before we participated in this year's contest, the previous world record was actually set by a very large Hadoop cluster of 2,100 nodes by Yahoo. And they sorted about 100 terabytes of data in 72 minutes on 2,100 nodes. So our entry, basically this is the new world record, tied with the UCSD one. We're sorting 100 terabyte in 23 minutes on about 200 EC2 nodes. Given the nodes are slightly better than the past one, but it's actually, by any measure, the old Yahoo cluster had a lot more resource than anything we could possibly have. So overall, we sorted 100 terabytes of data 3x faster, going down from 17 minutes to 23 minutes, and using a tenth of the nodes. And on a per node basis, I think it adds up to about maybe 30 times more efficient than the old record. And for the petabyte one, we didn't follow strictly the sort benchmark rules, so I don't think it's harder to find any comparison out there. But I put it up here just for your information. The sort rate happened to be the same. This is like purely coincidence. So why sorting? It seems like it's a lot more interesting to work on genomics and save lives. Like, what's special about sorting? Why would you ever want to sort a 100 terabyte or petabyte of data? The reason sorting is actually fairly interesting to us as developers of Spark is because sorting stresses this core operation called shuffle, which a lot of you, if you understand about MapReduce, you probably know what shuffle is. And shuffle is really a core operation in the whole sort of distributed computing paradigm that underpins everything from doing a large join in SQL that Frank talked about, all the way to doing machine learning, like recommendation algorithm that's communication heavy. A lot of the communication are done with shuffle. And sorting itself especially stretches shuffle because in sorting, to sort 100 terabytes of data, you will actually shuffle 100 terabytes of data. There's no reduction at all during the whole pipeline. To store 100 terabyte, you will read 100 terabyte from disk, shuffle 100 terabyte, and write 100 terabyte out. As a matter of fact, as I mentioned earlier, that sorting 100 terabyte, the minimum amount of I/O you will need to do is 500 terabytes of disk and 200 terabytes of network. So now, in the second half of the talk, I just want to talk about what make this effort possible. Like, how do we actually set a new record? I think the first thing I have to acknowledge is actually the rapid maturation of the cloud. This is, as I said earlier, this is the first time a public cloud-based system has won this benchmark. In a way, it sort of signifies how much the cloud infrastructure is mature. Because remember, this is both a benchmark on software and hardware. This would not have been possible even last year. So EC2, in a way, has matured significantly. The second is fairly important, which probably matters much more to the rest of the world here, there's a lot of engineering investment that have went into Spark about sort of handling very large scale workloads. And I'll talk about them in a bit. And then the third is, even with the first two, it's kind of hard to actually win benchmarks, especially when you're competing against state-of-the-art so academic prototypes. They are sort of highly optimized for doing this one thing. So we actually exploited a lot of the Spark's flexibility in programming model, and we have done quite a bit of clever techniques that I'll tell you more about. So first, I'm going to talk about basically just two major changes in the Spark networking layer. Sorbet Shuffle and the new sort of network transport that about the engineering investment in Spark to scale Spark out. The first is Shuffle. So the old Shuffle implementation in Spark is called hash-based Shuffle, which works surprisingly well for smaller data. But when we scale to very large data and when you want to have a huge number of tasks, Hash-based shuffle had a pretty serious problem. The problem is in hash-based shuffle, essentially you get a record, you have sort of output from your task, and you're trying to write them out directly to the what you call map output file. And each of these map output files, it's just a tiny chunk that's essentially partition of records, you write them out. In hash-based shuffle, you do a hash-based partitioning, and then you write the sort of your record out into the streams or onto files. And in order to write to files, as a Mac, this means it's actually a fairly random write process, because your first record might be writing to a number 1 block, and your second record might be writing to the third block, and your third record might be writing back to number 1. So you have a lot of seeks. Now, in order to mitigate the seeks, you will create actually in-memory buffers. So you batch all the writes, and up until a certain point, when you have enough writes, you flush them onto the blocks, onto file. Now, the problem is, if you have a huge number of blocks, i.e. a huge number of reduced tasks, it's actually very expensive to maintain all this in-memory buffer because they're all concurrent. And at some point, you just can't, you're bounded essentially by the number of, how much memory you can have to buffer all this stuff in order to sort of scale out your number of tasks. So this is actually, Matei himself did this work back about a few months ago, which is actually kind of a long time in Spark's release history. So there's a new Sorbet Shuffle. It's slightly different from Hadoop Sorbet Shuffle, but it's a new Sorbet Shuffle. They essentially sort the data based on the partition ID first, and then write them out. Essentially, what's going to happen is now that this pattern is, I'll write everything for sort of the block 1 first, and then everything to block 2, and everything to block 3, sort of sequentially. In this case, you only have 1 active stream at any given time, so it's actually have very low memory usage. And with this change, we could actually scale sort of the number of reduced tasks to a very high number. For example, in the Petabyte Sort, we had 250,000 reduced tasks, which is actually a very, very large number of reduced tasks if you ever run Spark or even Hadoop MapReduce. It's very rare you find a sort of very large scale job that one with this many reduced tasks. The second part is we built actually a whole new network transport layer. So there's 2 parts to Shuffle, right? One is how do you organize the data, how do you fetch them, and the second part is how do you actually transfer the data across network. So we rewrote essentially in Spark 1.2 the network transport layer based on Netty. Essentially, this is following some very common patterns that's doing event-driven architecture to get to high performance. And it's one neat thing here is I think a lot of this work are actually based on this thing called SEDA, which is the stage event-driven architecture, which also is just Matt Walsh's PhD thesis back in the 2000s at Berkeley. So we rewrote the network transport based on that, and we also started explicitly managing the memory of the network layer. So now, essentially, we're trying to manage all the network, because network you have buffers all the time. All these buffers actually creates quite a bit of memory pressure by the garbage collector and for the JVM. We essentially take all of those out and start managing all this stuff natively ourselves, so it doesn't get touched by the JVM. So with this new network transport layer, we were actually able to push the shuffle throughput to 1.1 gigabytes per node per second during shuffle. So this is essentially, so this is a chart from Ganglia. And Massey somewhere is going to be happy about it. This was measuring my about 200, slightly over 200 nodes. It's network activity, aggregate network activity when we're doing shuffle. Essentially, you can see it's, I ran the job twice, once with a slightly different config, but the second time I believe is the final run. And then it was going at close to 1.1 gigabyte per node per second, which is actually almost saturating the 10 gigabit Ethernet network. It's actually fairly hard for a general software to saturate a 10 gig link. On top of sort of what we have done changes to Spark, which would benefit everybody else, we also done some pretty clever, I think, techniques here. So I have to say, if our goal was to sort of beat Hadoop, I think the first tool would be sufficient. However, if our goal was to, actually try to win this benchmark, we knew we were competing against sort of purpose-built software, sometimes hardware. We had to push the boundary, and that's why we started doing some of the really interesting techniques to make it even more efficient. And a lot of this are actually based on the sort of the flexibility of Spark. It allowed us to do all this at the application level. First is, in order to actually optimize, really hyper-optimize the program, what you would focus for Spark is essentially, first thing I would probably do is to reduce GC, because you don't want the garbage collector to get in the way when you're trying to optimize, squeeze out like 10, 20% of the performance out there. If you spend 10% of your time doing GC, that's actually pretty bad, because you can gain 10% by getting rid of GC. So a lot of this is actually about that. Now, first of all, in order to get rid of GC, we started exploiting this thing called unsafe, which is a hidden, I believe, undocumented package in the JDK. Pretty much every JDK supports it now, even though the name is unsafe. Some of you probably know it's actually fairly safe to use it, with the caveat that it might crash your JVM. But it's when used well, essentially give you sort of random memory access as you wish, like the C-style pointers. So we use unsafe to actually pull all the data managed from the JVM heap directly to off heap. Now this way, the garbage collector doesn't even know about those data. So there's no GC happening here. And then we use unsafe to get to some more lower level sort of operation. Like for example, we can get 8 bytes of data at any given time. You can access to 64-bit memory address instead of the 32-bit arrays that are limited by the JVM. So let me clarify that. So the JVM arrays are sort of bounded to, I think, 2 GB in size, the byte array. If you use unsafe, you essentially have 64-bit addressing that you can do whatever you want. So with unsafe and pulling some of the stuff out of the JVM, we essentially observed no GC during our sort benchmark. And this is also coupled with a change I mentioned earlier, that in the network layer, we are now managing buffers explicitly. Spark is managing buffers explicitly rather than relying on the garbage collector. So now both the Spark level and the application level don't allocate any memory from a JVM GC point of view. Now, the second part is once you get rid of GC, you want to, it's a sort benchmark. The funny thing is once you optimize your sort selector, you will realize for a sort benchmark, the bottleneck is not about sorting. The bottleneck is actually O and I/O. But to get to that, if you just naively run, for example, a sort algorithm provided by the JVM or provided by the C standard library, you'll notice CPU it's probably CPU bound. It's actually not IO bound. But there's actually a lot of work in the past that, including the very classic alpha sort, also co-authored by Jim Gray himself, on how do you build very fast sorting, efficient algorithms. And a lot of it really goes down to just exploiting cache locality. So we, inspired by AlphaSort, we actually did some fairly simple tweaks to just how you would store and sort the data. So essentially, the naive way of sorting this data is you put, so by the way, each record is 100 bytes in the sort benchmark. So the naive way of doing it is you lay out just 100 bytes after 100 bytes, and you start sorting them based on the key you're supposed to compare. In this case, it's 10 bytes. So what we have done is actually we split the data into 2 parallel sort of arrays. The first one is just the data, which is your 100 bytes. And then the second one is a second array for each record only contains a 10-byte key, which is the key you actually need to compare for sorting. And then a 32-bit pointer, which means it's 4-byte pointer, pointing back to the address of the full 100-byte in memory. And this way, essentially, when you're doing sort of sorting, the following part might require you to refresh your memory about computer science 101. So sorting is mostly actually sequential memory access, if you can do it well. And essentially this way, we are applying sorting directly on the second array, which contains only the 10-byte keys and the 4-byte pointers, essentially 14 bytes per record. But for alignment purposes, we make them 16 bytes. So essentially each record becomes 16 bytes. And then you're doing comparisons directly on this 10-byte keys out of this 16 byte. So you're getting fairly good cache locality because as soon as you advance to the next record, very likely it's actually in the cache line, and CPU might have been prefetching it. So there are two benefits here. One is much higher cache locality, and the second one actually minimize data movement, because the only array we're sorting is the second array. So essentially, the data movement is we're just moving 14 bytes or 16 bytes when you take alignment into account. Moving 16 bytes per record, which means essentially 16 bytes per swap rather than 100 bytes. So once we do this, sort of fairly simple things, the whole sort of code for this is probably less than like 50 lines of code. We actually have a system that's very CPU bound. Essentially sorting, CPU can do it much faster now than we can read from this and all of that. So then we run into the next problem, which is in data parallel computation. You would notice one thing, which is especially for something that you can parallelize it very perfectly. You have a chart like this. Let's say you have just two cores. So you have 2 slots on each machine, and you're running the task. And so on the x-axis, just time. And then, so in the beginning, task 1 is reading a bunch of data from disk. Task 2 also get launched in parallel and reading a bunch of data from disk. And then once they finish reading their data, they need to start sorting. It might trigger external sort, but anyways, this is sort of the rough pipeline. You read, you sort, you write them out to the temporary sort of shuffle map output file. Now, the problem is if you're our sort algorithm is actually fairly efficient. So the second part is actually not that long, but it's mostly bounded by sort of the read and the write. And the problem is when task 1 and task 2 are both reading and writing, we are bounded by how much the SSDs or the disk can actually pull out of them. So it's on the nodes I was testing, they have like 3 gigabytes per second for all the SSDs combined on a single node. So this means when you have 2 tasks bounded by the same resource, which is I/O, if you run task 1 on its own, it's going to finish instead of whatever data you're reading divided by 3 gigabytes per second. But if you run task 1 and task 2 perfectly in parallel, it's going to bound it, each of them, by whatever you're reading divided by 3 gigabytes per second divided by 2, because they each get an equal share of the data set. And then, actually, to tell you just more about the details of this, what we found is on EC2, my guess is all the cores are sort of hyper-threaded. And then also for a very intensive sort benchmark, it's actually fairly cache-bound. So when you run the 2 sorts in parallel, even though all the data in memory, once you run them in parallel, leveraging all the 32 cores on those nodes, it's actually running slower than running 16 cores. So this sort of imply or suggests we should probably break them apart and exploit pipelining. What you really want is maybe for task 1 to read, and while task 1 is reading, task 2 doesn't really read. But as soon as task 1 finishes reading, task 2 can start reading. And then task 1 is doing sorting, so essentially now task 1 will complete the reading in about half of the time, and then task 2 can start reading also in about half of the time. And actually, the whole process would go faster if we start the pipelining like this. And so what we have done is actually we measure how fast the CPU, essentially what's the bandwidth the CPU can pull for sorting, and then we timed it, the ratio pretty well. So essentially we have, I believe, 16 tasks that's reading from the SSDs, and then the other 16 tasks is blocked on the other 16 tasks reading. And then once the first batch is finished reading, they start sorting, we start actually reading for the second batch of tasks. This way, we actually had a pretty good pipelining, and overall throughput actually improved. Even though it appears like not all the cores are being utilized at any given point. How do we do this? It might be hard to control if you know Spark well, but it's actually fairly easy. You just add a semaphore to the read. So you have a semaphore of 16, and then when the first 16 tasks come and it grabs the semaphore, the last 16 can't grab it anymore. So just to summarize, how do we set a new world record? A lot of the work is about the Spark itself. There's a lot of engineering work by both Databricks, AmpLab, and the Spark community to improve Spark. And but really, I think that gives us a huge win. I think already probably sufficient to beat Hadoop. But to really win this thing where there's a lot of purpose-built software and hardware systems being sort of provided to run the benchmark, we also leverage Spark's flexibility and added a lot of very clever sort of techniques at the user level to make this efficient. And then the end result is actually we had a system that was mostly hardware bound at each of the phase, basically at the map phase, which is a stage 1. It's mostly just reading and doing local sorting and partitioning. We're saturating, for each node, we had 8 SSDs and adds up to about 3 GB per second. We're saturating SSDs. And on the reduced phase, which is during shuffle and the actual sorting of the output, we're saturating the 10 gig network. So there's quite a bit of buzz about this. You might have seen in the media. But if you want to know more about some of the Spark part of the work, you can go to the CRL. I wrote a blog post about it. This is actually the first time I talk about some of the application level techniques. So hope you enjoyed it. And I know I'm the last one blocking you from going to food. So if there's anybody who wants to ask questions, I don't know do we have time for questions? Okay, so maybe a couple of questions. The only thing I could see is the Mac Apple logo. Yes. Use TCP, yeah. Oh, the question is, does the NATI transport use TCP under the hood? Yes, it uses TCP. And there's a follow-up. The instance type is I2AX large. Not in this one. I had a separate table that had it. It's I2AX large. It was a really expensive instance that doesn't have spot. So it's kind of, we spent a lot of money running this. Yes. Yes, they are all merged. Oh, the question is the new shuffle and all the new transport work, are they merged or contributed back to Spark? Yes. Everything we do for Spark, we merge it back to. Did I end up using Tachyon? We didn't use Tachyon in this one. It wasn't. I don't think it would make any difference because we mostly made it hardware bound. We wouldn't, because Tachyon is for managing like very large files. Like this is providing like random access and all of that. It's I don't think using Tachyon would, like Tachyon basically just have RAM disk on every node and let RAM disk manage it. Whereas it's actually fairly slow when you think about, so not Tachyon itself. For the purpose we want here, RAM disk management and defrag and all of those are actually kind of slow compared with just like a malloc. Yeah.
You used a 10-byte key, right? And then there was a 4-byte.
10-byte key and 4-byte array, 4-byte pointer.
So why not a 12-byte key so that it's like almost 16 complete?
Yeah, so we actually use 16-byte, and because JVM is signed, it's always signed, whereas when you're doing comparisons, it's actually lexicographic and it's unsigned on bytes. So we actually, just for the sake of ease, we only take we only use the first 7-byte in a long to do a comparison. So this, we never have to take into account the signed bit in the highest level. So, but I mean, it's basically the same. Like, all right, maybe one more, or maybe that's it. Yeah, I mean, unsafe essentially, the thing called malloc, I mean, it's an allocate memory and there's a free. It's essentially like, it's usually using the kernel malloc and all of that, I think. It's just using whatever Linux distribution you're using. And the one in Netty, the one for the transport one is an implementation similar to JE malloc. You could look it up if you want. It's called JE malloc. It's essentially like malloc for the JVM.
All right, great. Let's thank the speaker again.
Yeah, thank you.
All right, so just a few quick announcements. So yeah, it's the reception now. There's drinks and appetizers. That'll happen till 8 o'clock. I think it's just next door. A few other things. One, I think there's one of you, maybe this is an outdated announcement now, but one of you who borrowed a laptop from the Amp Lab, and I think that was in exchange for your car keys. So I think it's sort of a win-win to give back that computer if you haven't already. And then finally, day 2 starts tomorrow at 9 a.m., same place. And it'll consist of a bunch of additional talks and exercises. These new talks and the exercises will be focused on some really cutting edge, bleeding edge research going on in the Amp Lab. So thanks again. See you tomorrow.